Welcome to our first module of modeling and simulation. In this module, we will discuss what a model is and what it is not. And you will learn how to distinguish agent-based models from traditional mathematical models. We will also describe the modeling lifecycle. Let's go! So let's define what a model is. A typical definition is a simplification or abstraction of a situation or phenomena that can be used as a tool for predicting or explaining the behavior of something. Think about it in terms of role models. Role models are people whose patterns of behavior we identify, and then we emulate those patterns of behavior, or in terms of bad role models, we avoid those patterns of behavior. We can also think about models in terms of, for example, ecological models or scientific models. Here on the right side, you're seeing a model that shows the temperature versus the year in terms of observed temperature with human effects and natural forces only. And we use this model in order to predict what the Earth will look like in a number of years. So we use and we build those models in order to solve problems or to answer questions about a system or about a class of systems. We can, for example, build epidemiological models to predict the behavior of a virus over a number of days or weeks or months. And we can do the same with cybersecurity models, where we predict what the ramifications of a cyber attack are going to be like. Models are often limited to being just one mathematical equation. That makes them static. What we need from the model, though, is to show us different scenarios based on how we change the inputs. That's where simulation comes in. Simulation is a dynamic way of exploring a model's behavior when we make changes to the system. These changes help us build what-if scenarios. For example, what if we introduce vaccinations into an epidemic scenario? How will they change the outcome? What if we introduce antivirus software into a self-replicating virus attack? How will that limit the number of infected computers? What if we cut all emissions to zero? How will that affect global temperatures in 5, 10, and 50 years? Simulations help us answer these questions. So what makes a good model? The answer is simple and so hard. Focus. Focus, that is, number one, knowing how to formulate the central question of your inquiry, and number two, set boundaries around that central question so you don't get sidetracked by too much detail. That's the super hard part here. In other words, keeping the eyes on the prize means disregarding a whole lot of stuff that really isn't relevant to your model and leads to unnecessary complications. Here is an example. In America, many cities or communities put on Easter egg hunting events like this one during spring. Often there are over 200 kids, that is you plus 199 others, looking to capture as many as possible of the 500 candy-filled plastic eggs that volunteers have distributed in a park. All that within less than 5 minutes. Imagine yourself on the white starting line, about 1/3 into the field. 199 kids are facing south. You just don't know. Then the whistle blows. Where do you go to maximize your chance at getting the most eggs? Here is what this looks like in modeling language. The goal is to define a search strategy that helps maximize the number of Easter eggs found in a certain time span, here 5 minutes. Are the bushes and trees material to your search? Probably not, unless they conceal the location of an egg.
More importantly, though, we can learn that where one egg is, there must be another. So as soon as we walk over to capture one egg that we have seen, we know there must be more eggs nearby. What does this mean for our model? It means that we need to take into account the initial egg sensing path, then the radius for the nearby eggs. We will probably want the model to store the count of the found eggs, and the time elapsed since we found an egg can help us determine whether to change the direction of our egg sensing path in order to optimize the count of our found eggs. So these would be some of the necessary attributes for this model to store our information. Now let's talk about how we build such a model. This is where agent-based modeling comes in, because we want to track the path you as the agent are taking to maximize your Easter egg bounty. We will model eggs in clusters. If the agent in our model, which is you, finds an Easter egg, it switches to smaller scale movement. But if the time elapsed exceeds a threshold, it switches back to more straight movement. Speed plays a role only if you miss eggs when moving faster that you may have found when moving slower. And that is the very simple model. But then, how are we going to deal with the great unknown? All other 199 kids who also want to maximize the number of eggs found. To answer these big questions, we need to take a look at the larger model lifecycle. Here is how we're going to build our models. It is a structured process that we call the model lifecycle. The first step in our model lifecycle is to formulate a question that we're curious about, one that a dynamic model can answer. Such a question typically starts with how and asks about changes to a situation under certain conditions. For example, how would the number of winter highway accidents change if we put temperature-based access restrictions to the most dangerous highways into place? After that, we can start assembling hypotheses about how changes to, for example, the numbers of cars or trucks allowed on the highway during certain times of day, changes in speed limits, or changes in snow removal cycles could impact the number of accidents in the winter. Once we have decided which hypotheses to try out, we can start planning how we're going to model each one. And much of our modeling depends on how much different aspects like temperature, precipitation, speed, brake paths, and so on influence each other. The next step is to build the model and test whether the model works. But just a working model is not enough. We need to ask ourselves, do the results make sense? Do they help us understand the behavior of the system? Do they react as expected when we change the input parameters? And if not, why not? Usually, we have to formulate many hypotheses for what processes and structures are essential for the question or problem we address. We can start top down and ask ourselves questions such as, what factors have a strong influence on our question of interest? Are these factors independent or interacting? Are they affected by other important factors? We could draw flowcharts, influence diagrams, or other sketches of our system and question. The most important thing here is to start with the simplest approach possible, even if that is ridiculously simple. Then we gradually elaborate and refine the model, letting the factors and data lead us in how the final model fleshes out, not our preconceived ideas of what the model should look like. In other words, when we build a model, we are data explorers following this cycle, assumptions, implementation, output, analysis, interpretation, and revision. That cycle shows our learning curve. And now, on to agent-based models. We have already learned that agent-based models are different from simple mathematical models. They are dynamic and movement pattern-based. They consist of agents, that is, individual moving entities such as cars or people or bees in a beehive or children in an Easter egg hunt. Each of these entities, like the people, the cars, or the bees, or the children in an Easter egg hunt, have its own unique behavior and interact within its social group. Each agent is independent and adjusts their behavior based on their environment. Think of an agent-based model like a video game, for example, Minecraft or Stardew Valley. Your player's goal is to use the resources they find in this world to build shelter, find food, and craft tools to help them construct the universe they want to live in. They have to interact with the other characters they meet in the game and adjust their behavior based on those interactions or changes in their environment. For example, the weather, seasonal changes, and so on. Agent-based modeling is just like that, but in this course on a much smaller scale and with the goal to predict how agents are going to behave. In fact, the interactions with other agents in the environment, similar to as in Horizon Zero Dawn, fighting the enemy machines and striking allegiances with friendly tribes and outsmarting the unfriendly ones, is at the core of the agent-based model. Just like in a video game where you have at certain points the choice of what path of action to take, we build points into our simulations in which we change what the environment does or what the agents choose in order to see how these choices influence the outcome of the model. But let's listen to one of the inventors of agent-based modeling himself.
Hello. So now that we've started to explore agent-based modeling a little bit more, and we've gone over what the class is going to be about, let's take a step back and let's go back to discuss what an agent-based model is in the first place. But before we discuss what an agent-based model is, I think it's important to discuss what a model is. And I find this important because in many ways, understanding an agent-based model involves understanding what the point of modeling is to begin with. And this is something that many of you may have learned at some point in your careers, but it's important to kind of take a refresher and take a step back and discuss this. So I define an agent-based model as an abstracted description of a process, object, or event. And the important point here is that it's abstracted. It's not a perfect representation. It doesn't exactly match up with the real world, and the important thing is that it exaggerates certain aspects at the expense of others. So, for instance, in this particular slide, I have a picture of the Earth, and imagine that this is actually the real Earth that you're trying to model. And on one side, we have a particular projection onto a two-dimensional map of the Earth. And what that allows you to see very easily is kind of the delineation between where the Earth is land and where it's water, though of course that'd be changing in time, as you might expect. But it doesn't allow certain other aspects. For instance, it doesn't really talk about what's inside the Earth. On the right-hand side, I have an image that you might see from a traditional intro to Earth science textbook or something along those lines, where we show a cutaway of the Earth and we can kind of see what the crust is and what the other aspects are. Now, neither of these models is a perfect model, right? Both of these models are wrong to some extent. And in fact, George Box, a famous statistician, had a quote to that interpretation, right? That essentially all models are wrong, but some are useful. The perfect model is not the model that best represents the world around us, but instead is a model that in some ways exaggerates the aspects of the world that we're most interested in and can help us solve the problems that we're looking at. In fact, my advisor, John Holland, used to say that models are in some ways like political cartoons, right? They exaggerate and blow up certain aspects while backgrounding and hiding other aspects for you to make, so that you can concentrate on the aspects that they're trying to make a point about. So given that description of a model, right, then what is an agent-based model? Well, an agent-based model in our context is a model that's composed of agents, as you might expect. And an agent is an autonomous individual element with properties and actions in a computer simulation. So we're in most of the context we're going to talk about, at least, is in a computer simulation. And agent-based modeling is the idea that the world itself can best be modeled by using agents, an environment, and a description of agent-agent and agent-environment interactions. And the central conceit of agent-based modeling, right, is that this is one of the best ways to describe a lot of the complex systems that we see around us. Now, over here, I have some descriptions of some different types of things that we might think of agents. Now, generally, when people think of agents, they often think of humans, right, and individual humans in that context. But an agent doesn't have to be an individual human. It could be a company, for instance, in which case the agent-based model might be a model of the interactions between the different companies. It could, in fact, be a human. So in this graph right here, I actually have a screen capture of the NetLogo HIV transmission model, in which case the model is, in fact, of agents who are representing humans who might spread HIV from one to the other. Now, note, especially, there was no reason why the model had to have been built at the level of humans. It was probably appropriate for the particular purposes for which the model was being constructed, but it could have been built at the level of, say, for instance, viruses, right? In which case it would be a very different model and at a different level of resolution and would probably help you answer different questions. A model could also be a government. So here I have a representation of the Capitol Dome in Washington, D.C., right? And we could instead be modeling the interaction between governmental agents. Now, over here, I have a representation of Kim Jong-il, right? And I put Kim Jong-il up there not as an indication of what you might represent with an agent-based model, but as a representation of what it's often not useful to represent as an agent-based model. So many agent-based models try to characterize overall patterns of behavior, right? And when you have one individual who in many ways is kind of erratic, is different from the overall behavior, it's very hard to kind of predict or understand what that individual is going to do. Now, in those cases, there are other modeling approaches, such as ethnographic modeling or in-depth psychological studies that might give you better understanding. But in many cases, I suggest not using agent-based models for these. On the other hand, if you wanted to build a set of agent-based models in which you tried to understand the role of dictators and despots and something like along those lines on a more kind of generalized basis rather than for one particular individual, then agent-based modeling might very well be useful for that context.
So what does all of this mean for our Easter egg hunt, and how can you maximize your egg bounty? Depending on how we model it, our model will most likely show us that if 199 children run south, it will be smarter for you not to run south, but to run north. This will guarantee that if the eggs are evenly distributed across the entire field, you will end up with more eggs than anyone within the available 5 minutes. So to summarize, you have learned that a model is a purposeful simplification of a system for solving a particular problem or category of problems. We use agent-based models when we think it is important for a model to include the system's individuals and what they do. Our modeling cycle goes through the following stages: formulating a precise question, assembling hypotheses for key processes and structures, formulating the model by choosing appropriate scales, entities, state variables, processes, and parameters, implementing the model in a computer program, and analyzing, testing, and revising. And here then is what you have learned. You have learned to define what a model is and what it is not. You have also learned what the difference is between traditional mathematical models and agent-based models. And finally, you have learned what our modeling lifecycle looks like. Thanks for watching. I look forward to seeing you again in the next video.